Humanity's story is inextricably linked to its quest for energy. From the first controlled fires that warmed our ancestors and cooked their food, to the harnessing of wind and water, and later the monumental power unlocked from fossil fuels and the atom, our civilization has been built upon an ever-increasing appetite for power. This relentless drive has propelled us forward, enabling technological marvels, global connectivity, and societies of unprecedented complexity. But this progress has come at a considerable cost, tethering our future to finite resources and altering the very climate of our planet. The search for a clean, abundant, perpetual energy source remains the single greatest challenge of our time. We have looked to the sun, capturing a minuscule fraction of its output with solar panels spread across our world. We have split the atom and dreamed of fusion, attempting to replicate the stellar furnace here on Earth. Yet what if we could bypass these terrestrial imitations and go directly to the source? What if, instead of merely catching the faint sunlight that reaches our small planet, we could harvest the colossal, unbridled energy of a star itself? This is not a question of simple solar panels, but of a technological endeavor so vast it borders on the mythological. The concept of stellar husbandry, or star farming. Imagine a future where our energy needs are no longer a point of geopolitical tension or environmental concern. A world where the power output of an entire star is at our command, channeled across the void of space to fuel our cities, industries, and explorations. Such a concept transcends our current understanding of engineering, economics, and even societal structure. It forces us to think not in terms of megawatts or terawatts, but in stellar orders of magnitude. This thought experiment is not a journey into science fiction, but a sober exploration of engineering on a scale never before contemplated. We will set aside faster-than-light travel and exotic physics, grounding our inquiry in the known principles of science. Our goal is to ask a simple, yet profound question. If humanity were to collectively embark on the project of harvesting a star, what would really happen? The consequences would ripple through every facet of our existence, reshaping our world in ways we can only begin to calculate. Before we can explore the consequences of farming a star, we must first define what such an audacious project would entail in practical physical terms. For the purpose of our analysis, we will assume the most plausible approach, a Dyson swarm. This is a vast constellation of independent solar collectors and habitats orbiting a star. This choice is rooted in engineering reality. A solid sphere would be gravitationally unstable. A swarm, however, could be built incrementally, with each satellite acting as an individual power plant. These collectors would absorb raw stellar radiation, light, heat, and energetic particles, and convert it into a usable form, most likely electricity or focused energy beams. The sheer scale of this is difficult to comprehend. It would necessitate manufacturing and launching perhaps trillions of autonomous satellites, creating an artificial celestial body of our own making. We will assume the target is a stable, relatively small star, like a K-type or M-type dwarf, to minimize radiological hazards and gravitational complexities. Our focus is not on the fantasy of the outcome, but the brutal reality of the process. This investigation will therefore follow the logical progression of such a multi-generational endeavor. We will begin by examining the initial steps: immense resource mobilization and manufacturing challenges. From there, we will trace the cascading effects on global infrastructure, geopolitics, and human society as the project matures and the first trickles of stellar energy begin to arrive. This is the story of humanity's greatest attempt at engineering, a project so large it would redefine our species' relationship with the universe itself. The decision to construct a Dyson swarm would trigger the most extensive resource mobilization in human history, dwarfing all previous endeavors combined. To build the swarm, we would need to mine and process astronomical tonnages of iron, silicon, aluminum, and other essential elements. Entire mountain ranges would be leveled. This wouldn't be a project for a single nation. It would demand planet-wide redirection of our entire industrial capacity for generations. This great scramble would immediately and permanently reshape the global economy. The value of raw materials would skyrocket, turning previously marginal deposits into strategic assets of immense worth. Nations and corporations controlling these resources would gain unprecedented geopolitical leverage, a new world order not defined by oil or data, but by access to bulk industrial metals. The environmental consequences of this planetary-scale extraction would be severe and immediate. The energy required to mine and refine these materials would cause a massive initial spike in carbon emissions. We would be sacrificing significant parts of our own planet's health as the down payment for an energy-rich future, a trade-off with profound ethical implications. This mobilization would require an unprecedented centralization of labor and automation. To meet the production quotas, nearly every manufacturing sector would be absorbed into the swarm supply chain. Society would transform into a singular, purpose-driven machine, where individual careers and national economies are all subservient to the singular, multi-generational task of feeding the swarm's ever-growing appetite for materials. Once the components are manufactured, humanity would face its next great obstacle, the tyranny of the launch equation. Every kilogram we send to space requires huge energy to escape Earth's gravity. Chemical rockets would be woefully inadequate. This forces entirely new launch infrastructure, most likely non-rocket systems like massive space elevators, or orbital rings, vast active structures in low Earth orbit able to fling payloads to higher orbits or interplanetary trajectories. The logistics would be mind-boggling. A continuous stream of material would flow from Earth to orbital assembly stations. Imagine millions of automated climbers ascending multiple space elevators, 24 hours a day, for centuries. These orbital stations would become sprawling factories in space, assembling the swarm satellites. Those satellites would be pushed out of the solar system on slow, efficient trajectories toward the target star, a journey that could take thousands of years, forming a river of hardware through interstellar space. This creates a long period of energy austerity on Earth, humanity living in the shadow of its ambition, enduring a lower standard of living now for the promise of infinite energy later. After centuries of construction and millennia of transit, the first wave of swarm satellites finally arrives at the target star and begins deployment. Now comes the central challenge, transmitting this power back across interstellar distances. The most plausible method would be a highly focused beam of energy. The receiving station would need to be colossal, a rectenna spread across millions of square kilometers to capture the faint signal. That receiving dish becomes another megastructure. This process is monumentally inefficient. A yottawatt at the star might only deliver a few terawatts of usable power to the global grid. The first trickle of star power would be a whisper, not a roar. This shift would trigger an unprecedented wave of economic centralization. The Swarm Authority, a transnational consortium, would become the sole source of primary energy for the entire planet. The planet's surface would slowly deindustrialize. Earth's role would shift from being the center of production to being a residential and biological preserve. The system-wide impact would culminate in a complete redefinition of human society and the very purpose of work. With food, shelter, and energy guaranteed, people would be free to pursue education, art, and research. After millennia of upheaval, humanity would settle into a new, stable equilibrium. The world would be defined by post-scarcity. Earth would be quieter, cleaner, and more ecologically stable. This stability, however, would be built upon a foundation of absolute centralization. The risk of tyranny would be coded into the very infrastructure of civilization. The human experience itself would be bifurcated. A planet-bound population would live in a world akin to a global nature preserve, while a significant portion of humanity would live and work in orbit. The species would have a single point of failure. This makes the civilization incredibly robust against terrestrial problems, but terrifyingly vulnerable to a single catastrophic failure in its cosmic infrastructure. The new baseline for humanity is one of quiet, managed prosperity, forever living in the shadow of its own greatest creation. The grand thought experiment of star farming, while seemingly a distant fantasy, offers profound and practical lessons for our present. The primary insight is a deeper understanding of scale and consequence. A second crucial takeaway lies in the paradox of centralization. It teaches us the inherent value of decentralization, resilience, and diversity in our critical infrastructure. Furthermore, the scenario forces us to confront the future of work. The question of what humanity will do when traditional labor is no longer necessary is not one for a far-off future, but one we must begin to answer now. In the end, the journey to harvest a star reveals that our greatest challenges are not technical, but human. Our ability to cooperate, to manage power without corruption, and to build a future that is not just prosperous, but also meaningful. What scenario should we explore next? Share your ideas below. You've been watching IfVerse, where imagination meets possibility. See you in our next reality.